The topic of this chapter is chemical bonds. Between two or more atoms, there may be interactions between them to lead to the formation of an aggregate with sufficient stability. Such interactions are called chemical bonds. Chemical bonds make it convenient for the chemist to consider the aggregate as an independent molecule. Chemical bonds also stabilize ions with two or more nuclei called molecular ions. All atomic nuclei have positive charge and repel each other with electrostatic force. Thus, a chemical bond must be made of electrons, which have negative charge and attract the nuclei. Born-Oppenheimer approximation is the assumption that the motion of atomic nuclei and electrons in a molecule can be treated separately, based on the fact that the nuclei are much heavier than the electrons. Consequently, when considering the chemical bond, the nuclei are regarded stationary. The neglect of the motion of the nuclei is the so-called clamped nuclei approximation. The simplest molecule or molecular ion is dihydrogen cation or hydrogen molecular ion. It consists of two hydrogen nuclei, protons, sharing a single electron. The two fixed protons are labeled 1 and 2. The distances between the electron and the nuclei are denoted R1 and R2. The electronic Schrödinger equation is shown below. The electronic Hamiltonian contains the kinetic energy of the electron and electron nuclear Coulomb potential energy. An additive term, the constant Coulomb nuclear potential energy, has been omitted, since it merely shifts the energy. Unfortunately, this Schrödinger equation does not have an analytical solution. In other words, the form of the wave functions and their associated energies cannot be found. In 1929, Sir John Lennard Jones introduced the linear combination of atomic orbital or LCAO. LCAO is a quantum superposition of atomic orbitals and a technique for calculating stationary states and corresponding energies in molecules. For dihydrogen cation, the LCAO would be as follows. Psi1 and Psi2 are the orbitals of hydrogen atom 1 and 2, respectively, which are exactly known. Coefficients C1 and C2 are the weights of the contributions of the atomic orbitals to the LCAO. Pay attention to that, a LCAO is not the exact solution to the Schrödinger equation but an approximation. Nevertheless, the wave function can be substituted by this LCAO to the Schrödinger equation, so that the Schrödinger equation will read like this. Then, some treatment is done to the equation. First, multiply the equation by the complex conjugate of Psi1 from left. Second, integrate the equation in the whole space and expand the definite integrals, bearing in mind that C1, C2 and E are just numbers. Third, use notations to denote the definite integrals. For example, the first definite integral is called the Coulomb integral, denoted with H11. Similarly, the exchange integral and the overlap integral are defined. Finally, the atomic orbital itself is normalized. With the notations, the previous equation can be written in the following way. The process can be repeated starting with multiplying the equation by the complex conjugate of Psi2 from left, and then integrate in the whole space. With similar notations of Coulomb integral, exchange integral, overlap integral, and the normalization of wave functions, that equation reads like this. These two equations are linear equations about C1 and C2. It is often convenient to represent them as a matrix equation, in which the square matrix is called the coefficient matrix of C1 and C2. The linear equations have a unique solution if and only if its coefficient determinant is non-zero. But this solution is trivial because both C1 and C2 are zero. That would imply that LCAO is zero, which is no good. Thus, to have non-zero LCAO, the coefficient determinant must be zero. The equation obtained by equating the coefficient determinant to zero is secular equation. If the two atomic orbitals in LCAO are the same type orbitals, the secular equation can be further simplified due to the symmetry of the system. The two Coulomb integrals are identical. The two exchange integrals are identical. The two overlap integrals are identical as well. For simplicity, they are denoted by alpha, beta, and s. Then, the secular equation becomes a simple quadratic equation about energy. This quadratic equation has two solutions. They are denoted as E plus and E minus, both of which depend on the values of the integrals, while the values of the integrals depend on the distance between the protons. The relationship between C1 and C2 can be found by inserting the energies to the previous equations. If E plus is used, C1 is equal to C2. They can be denoted as C plus. This LCAO is denoted as psi plus. If E minus is used, C1 bis equal to minus C2. C1 can be denoted as C minus, then C2 is minus C minus. This LCAO is denoted as psi minus. It is not difficult to find that the number of linearly independent LCAOs is equal to the number of atomic orbitals included in the linear combination. To find the values of C plus and C minus, the normalization condition is used. That is, the total probability of finding the electron in the whole space is 1. Note that the probability density of finding the electron is the square of the modulus of the wave function. There are 4 definite integrals in the calculation. 2 of them are the normalizations of atomic orbitals. The other 2 are the overlap integrals. So, C plus minus can be expressed with the overlap integral. The final LCAOs are shown as follows. The values of the LCAOs made from the 1s atomic orbitals on the x-y plane are shown here. The distance between the nuclei is set to twice of Bohr radius. Psi plus is called the bonding orbital. In the case of bonding orbital, the atomic orbitals enhance each other between the two nuclei. Psi minus is the antibonding orbital. In the case of antibonding orbital, the atomic orbitals cancel each other between the two nuclei. The probability density distributions of the electron in the LCAOs are shown here. In the case of bonding orbital, the electron has a higher probability to be found between the two nuclei. It attracts the nuclei towards the center. The attraction could balance the repulsion between the nuclei, so the system is stabilized. This attraction forms a chemical bond. In the case of antibonding orbital, there is a lack of electron between the nuclei to balance the repulsion between them. The electron even pulls the nuclei apart. So, the system is not stabilized. The total energy of a molecule or molecular ion is the sum of the electronic energy and the electrostatic potential energy between the nuclei. They both depend on the positions of the nuclei. The potential energy surface describes the total energy of the system in terms of the positions of the nuclei. For example, the potential energy surface of water molecule is the total energy of water molecule in terms of the angle and distances between the nuclei. In the case of LCAOs of dihydrogen cation of 1s atomic orbitals, the total energy depends exclusively on the distance between the protons. In this case, the potential energy surface is an energy curve. The energy curve of the bonding orbital has a minimum. The distance corresponding to the minimum energy is the equilibrium distance, that is, the bond length. When the distance is infinity, the energy is the energy of the 1s orbital, denoted as E1. The difference between the minimum energy and the energy at infinity distance is the binding energy of the bond. According to LCAO, the ground state of dihydrogen cation has an equilibrium distance about 2.5 Bohr radius and a binding energy about 0.13 E1. However, experiments show the equilibrium distance of 1.44 Bohr radius and a binding energy of 0.2 E1. It suggests that LCAO is not very accurate. Nevertheless, it qualitatively explains the formation of chemical bonds. LCAOs and chemical bonds are classified based on their symmetries. A sigma orbital is cylindrically symmetric with respect to the bond axis, which is the straight line that connects the nuclei bonded to each other. For example, the 1s orbitals are cylindrically symmetric with respect to the bond axis. So, their combinations are cylindrically symmetric with respect to the bond axis as well. Therefore, both the bonding and antibonding LCAOs of 1s orbitals form sigma orbitals. The bonding orbital is denoted as sigma-1s, while the antibonding orbital is denoted as sigma-1s with an asterisk at the superscript. The electrons in sigma-1s orbital form a sigma bond. The bond axis is usually selected as the z-axis, so the pz orbital is cylindrically symmetric with respect to the bond axis. Thus, the combinations of two 2pz orbitals are sigma bonds. The bonding orbital is denoted as sigma-2pz, while the antibonding orbital is denoted as sigma-2pz asterisk. For the same reason, the combinations of an s orbital and a pz orbital are cylindrically symmetric with respect to the bond axis and are sigma bonds. Whether an LCAO is bonding or antibonding depends on if there is a high probability to find the electron between the nuclei. A pi orbital has one mirror reflection symmetry with respect to a plane containing the bond axis. For example, a 2px orbital has a mirror reflection with respect to the zx plane. So, the combinations of two 2px orbitals have mirror reflection symmetry with respect to the zx plane as well. They are the bonding and antibonding pi2p orbitals. Similarly, the two py orbitals form the bonding and antibonding pi2p orbitals. They have mirror reflection symmetry with respect to the yz plane. There are other types of orbitals with different symmetries, but the sigma and pi orbitals are by far the most common and important orbitals.